So we start here from where we left off in the last class, right? So last class we talked up to the supernova. So what happens in the supernova? Subatomic particle fusion occurs that causes a large explosion, and so electrons are pushed into protons. That causes a subatomic particle fusion, which releases huge amount of energy, and so the red supergiant explodes. And when the red supergiant explodes, the process is called a this explosion process is called a supernova. Okay, and what happens after the supernova? That's what we will study in today's class. What happens after the supernova? So after the supernova, now understand which star what happens when a star actually like explodes. Like supernova only occurs from supergiant, right? Specifically red supergiant. So supernova must occur from a red supergiant. And one thing about red supergiants is red supergiants are not formed from average stars, right? For example, the average sun. If you remember this diagram, the average star, the sun, this will never become a red supergiant and there will never be a supernova, right? We studied this life cycle, all of it, from nebula to average star all the way to white dwarf. But there was no supernova in the life cycle of the average small star, right? The average star, the small star, the low mass star, the average mass star, or the low mass star. For example, our sun. So our sun will never explode into a supernova. It will become a red giant and then kind of explode into a planetary nebula and then become a white dwarf. But when the star is massive, the massive stars become a red supergiant and then they explode into a supernova, right? Okay. So after the supernova, since it was a massive star, the remaining part, you see the supernova has like lots of debris all around it, you can see that, right? There are lots of debris around the supernova, correct? So there will be some parts remaining after the supernova, right? This is called the core remnant. Okay, so that's what we're talking about, that any matter remaining, this any matter remaining is actually called core remnant. Okay, core remnant, remnant as in remaining parts or remainings, and core remnant, so remaining parts of the core will form a very dense neutron star. Okay, so this is interesting. We studied normal stars, we studied white dwarfs. Do you remember what's the difference between normal stars and other planets and white dwarfs? White dwarfs are composed mostly of nuclei only, right? Nuclei only, white dwarfs. And before a neutron star is formed, what happened? A supernova. The fact that a supernova happened, what does this indicate? This indicates that subatomic particle fusion has occurred, right? Because without subatomic particle fusion, there will not be enough energy released to cause a supernova, right? So the fact that a neutron star has formed, that means it has come from a supernova, and that means subatomic particle fusion has occurred, right? Now why is the neutron star called neutron star? I think you can guess it already. Try to guess it. What's happening here? Why is it called a neutron star? Because what is a subatomic particle fusion? In subatomic particle fusion, electrons are pushed electrons are pushed into protons, right? Electrons are pushed into protons to form what? To form neutrons. So as electrons are pushed into protons to form neutrons, that's subatomic particle fusion. So after the supernova, what is remaining in the core? Understand, what is remaining in the core remnants, because the other parts, the debris that you see all around it, the broken pieces and stardust and broken pieces of the star, those parts will be atoms. There will be atoms, there will be protons, there will be electrons, there will be also be neutrons, there will be the other elements. The debris around you see the debris around it, around the supernova, whatever spreads out from the supernova, those will call those will contain all the elements that are formed by so many fusion reactions, and then from the supernova, due to subatomic particle fusion, a lot of elements will be formed. All of those elements will make up the debris, the stardust, the broken pieces of the star from the supernova. However, this subatomic particle fusion will this subatomic particle fusion will mostly occur where? Where will most of the subatomic particle fusion occur? Well, most of fusion occurs where? At the core of the star. Why at the core? Because it has the highest temperature and pressure, right? Similarly, subatomic particle fusion will also occur right at the core of the star, at the center of the star, like at the center of the supernova in this case. So the neutrons that are formed, as electrons are pushed into protons to form neutrons, as these neutrons are formed, they will stay where? Where do you expect to find them? The neutrons that are formed from the subatomic particle fusion, where do you expect to find most of those neutrons? In the core remnant. Most of those neutrons you're gonna find in the core remnant, right? Because that's the remaining parts of the core. Any matter remaining, core remnant. Okay, let's ignore the very dense part for a second. We'll form a neutron star. Okay, we'll form a neutron star. Now, so far so good? Any questions thus far? The core remnant will form a very dense neutron star. I haven't explained the very dense yet, but neutron star. Okay, any questions? Let's see. I will send the updated PDF version, hopefully after this class. Yeah. Massive star থেকে direct supernova হতে পারে না. No. For a supernova to occur, the core of the star must become iron. Because until the core becomes iron, you see, until the core becomes iron, there is always enough energy, temperature, pressure to trigger the next stage of fusion. But nuclear fusion of iron is impossible. The fact that fusion of iron is impossible, that is why only after the core is iron, subatomic particle fusion occurs and a supernova takes place. So supernova cannot directly form from directly form from the massive star. It has to form from the red supergiant. Now there might be exceptions or there might not be. I'm not sure about that, but I'm like I'm con this supernova that you're studying, this life cycle, this is called a type 2 supernova. Okay, so I haven't studied type 1 supernova in depth either, so like because it's not in your syllabus, and it has not been in my syllabus either. But if we come across it, like ask me later outside the class. I don't want to like spend time on that in the class time. Okay, now any matter remaining, the core remnant, will form a very dense neutron star. Okay. Oh, any more questions up to this point? Any more questions? Uh, core remnant. No, we are saying core remnant and not just core, because it's like if you take a piece of chocolate like that you just bought, that's a piece of chocolate, right? But then you leave it on the table, and then your little brother gets like a bite on it and leaves like a little part for you. Is that chocolate, or is it the remnants of the chocolate? It's the remnants of the chocolate. Okay, like that. In the supernova, most of the star, and even most of the core is like broken into pieces, distributed in the space in the supernova nebula formed. Okay, but some remaining parts of the core that we are calling core remnants, that will form the neutron star. Does the core provide all the energy? That's a very good question. Does the core provide all the energy? Nuclear fusion provides all the energy in a star. Okay, nuclear fusion actually provides all the energy. So if it's most of the nuclear fusion reactions, the majority of the nuclear fusion reactions, the fastest, more energetic fusion reactions occur at the core. However, lower stages of nuclear fusion reactions does occur throughout the other places of the star and even at the surface. For example, even when, let's say, a red giant, not red supergiant, red giant, the average star's second phase. So on the red giant, I told you that at the core of the star, or at the core of the red giant, which fusion is taking place? Helium fusion. If you remember, helium fusion is taking place at the core of the red giant. But at its surface, some hydrogen is still remaining, and those hydrogens are still fusing into one another. So some hydrogen fusion is still occurring on the surface, but the majority is at the core, and that is helium fusion. So yeah, the star gets most of its energy from the core, but nuclear fusion actually, the a star gets its energy from nuclear fusion. Now wherever it takes place, now most of those take place in the core. Okay, the more energetic ones, that is. Okay, so what is the yeah? Why a star does have to die? What is the problem? Well, laws of nature, laws of physics, gravity. That is what we are talking about, right? Why the star has to die? Because its fuel runs out, right? And then as its fuel runs out, it contracts because of gravity. And then as gravity takes hold, then there is again enough energy to basically burn new fuel, that is helium, and then there is enough energy to burn new fuel like lithium and so on. So yeah, it's just the natural laws of physics. Is it mandatory to form a red giant? No. An average star will go from main sequence star to a red giant phase, but Okay, we had some technical issues, but I think we're back online now. You can view it. All right, let's check. Okay. All right. So, is it all right for you guys now? It started again. What started again? Oh, it started lagging again. Okay, there is way too much lag. I think it's okay. Um, is it all right again now? Yes, for now. Okay. Okay, I think it's okay now. Yeah, 9 viewers. So yeah. Okay, so let's get back to the content. Now, like I was saying, I'm going to answer the last question again and then move on to the next topic. But what was the last question? What was I saying? Is it mandatory to form a red giant? No, it's not mandatory. A star can become if an average star becomes a red giant, but a massive star becomes a red supergiant. So it depends on the mass. So not every star will become a red giant. Okay, why is the sun considered a star? Really? Because it's a star. What are the okay? Because it fits the characteristics of a star. What are the characteristics of a star? Like, what will you call a star? What is a star? A star is a hot ball of gas that generates its energy by nuclear fusion reaction. A huge ball of gas in the in space that generates its energy by nuclear fusion reactions. And the sun that we see in the sky happens to be just like that, just like many others. So it's a star. Okay. Um, কম্পিউটার দিয়ে কমেন্ট পোস্ট করতে পারতেছি না কেউ সলিউশন জানো no actually this is weird. I'm not sure Rafin why you're having this issue. Yeah, okay, I just answered why the sun is a star. Now let's get back to the actual let's get back into it. No, now there is no lag Shahriar. I'm saying I think the lag is gone now. Yeah, I'm not saying anything. I like the slide is not moving or anything. So okay, anyway, like I said, any matter remaining will form a very dense neutron star, right? Okay. Now, why is the neutron star very dense? Do you remember why the white dwarf was very dense? Well, the white dwarf was very dense because it was composed of mostly nuclei, right? Well, the neutron star is composed mostly of just neutrons. Now think about it. Now think about it. Like um right like most of the protons in a neutron stars convert into neutrons, right? Neutron stars are like made up of about 95% neutrons, all right? It's like mostly neutrons. Okay, so you may ask, but the star had protons, neutrons, and electrons. How did the protons become neutrons? How did the protons become neutrons? What do you think? The answer is how did the protons become neutrons? Well, by the supernova. In the supernova, electrons were pushed into protons to form neutrons, and that's how by subatomic particles, by subatomic particle fusion, and that is how, like, are you guys getting buffering again? I'm not sure. Anyway, so that is how you get basically that's why the neutron star is composed just mostly of neutrons. Now think about it. Nucleus is much more dense, millions of times dense than the atoms, right? But neutrons, only neutrons, because a nucleus is even composed of protons and neutrons. But if you remove even the protons and only the neutrons, you take only the neutrons, then it's much more dense. Okay, a neutron star is even slightly more dense than a white dwarf star. Okay, so the neutron stars are the most dense objects in the whole universe. All right, is the connection better now? Can you guys please check? Is it still buffering? I think it's kind of okay now. Can you guys hear me now? I think it's alright now. Okay, let's continue. So, but if you get back to this diagram, we saw that from a supernova, it's not necessary that always a neutron star will form. From a supernova, even a black hole can form. So what's a black hole and how can that form? You see, the neutron star, since it's the most dense material in the universe, it's the densest object in the universe, it's the most dense object in the whole universe. So the neutron star actually has a something called a limiting value. Okay, neutron star has something called a limiting value. All right. So the limiting value for a neutron star. Okay, why is it lagging so much? We're having quite a lot of connection issues. Please have patience. Okay, we are finally back online. All right. So, like we were saying, let's continue from where we left off. I will repeat what you missed. Don't worry. Okay. So, like I was saying, the neutron star is basically, when does a neutron? How does a neutron star form? Like, what does it form from? It forms from the core remnants. The core remnants after the supernova, right? So after the supernova, the any matter remaining that we will call the core remnants, it will form a very dense neutron star. Okay, and when it forms a very dense neutron star, since it's formed from the supernova, the neutron star is composed mostly of just neutrons. Why mostly of just neutrons? Where did the protons disappear? Well, the protons have been converted into neutrons because of subatomic particle fusion, right? Because electrons have been pushed into protons to form neutrons, which is called subatomic particle fusion. So due to the subatomic particle fusion, the neutron star is composed only of neutrons. Alright, now as we continue to the next point, now the neutron star itself has a limiting value. Okay, and the limiting value, there the neutron star has something called a limiting value. So what is the limiting value? It has a limiting value of a mass. The neutron star, the limiting value for a neutron star is 1.5 to 3 solar masses. Now do you remember what solar mass is? Solar mass? Solar mass is a unit of mass, right? It's a unit of mass. It's a just large, very large unit of mass, just like light year is for distance, a large unit of mass, a large unit of distance. Similarly, solar mass is a large unit of mass. One solar mass is the mass of our sun, which is 2 times 10 to the power 30 kg. So now understand, the limiting value of the neutron star is 1.5 to 3 solar masses. Okay, now I want you to focus here. Okay, like this is very, very important. This 1.5 to 3 solar mass, this 1.5 to 3 solar mass is the mass of the core remnant, right? Just the remaining parts. This is not the total mass of the star. The total mass of the star is much, much larger. 1.5 to 3 solar mass, what does it mean? It means like meh, 1.5 times the mass of the sun, or like 3 times the mass of the sun, right? So it's like um, 3 times bigger than the sun. So just the remaining parts of the star, after all that supernova, after throwing out most of its parts into the into the empty space as just debris and nebula, stellar nebula, the whatever remains after the supernova is the core remnant. Just that core remnant, that forms the neutron star, and the mass of that core remnant can be about 1.5 to 3 solar mass. This is the limiting value. Okay, okay, so this is the limiting value. So that's very important. The limiting value for a neutron star is 1.5 to 3 solar masses. Now let me make this separate point. this is the this is the mass of a neutron star resulting from a star of 15 to 20 solar masses. 15 to 20 solar masses. So the biggest neutron star will be about 1.5 to 3 solar masses, and that's just the mass of the core remnant and the mass of the original star that this neutron star resulting from a star. You have to understand this neutron star, this is formed from the core remnant, but the original star was much bigger because the original star was a supermassive star that became a red giant, and then there was a supernova and most of the star parts were just given away into the empty space, and then only a small part remained. So the small part that remained is about 1.5 to 3 times the mass of the sun, that is 1.5 to 3 solar masses, and the original star that this neutron star resulting from, the original star was about 15 to 20 solar masses. So the original star was about 15 to 20 times the mass of the sun. Alright, so the original star was that big. So the original star was 15 to 20 times the mass of the sun. Then the core remnant core remnant formed neutron star will be about 1.5 to 3 solar masses. This is the maximum limiting value for a neutron star. So now that you understand the limiting value, what will happen if the core remnant, what will happen for an even bigger star? Like this is, I'm talking about 20 times the mass of the sun, 20 solar mass. What if the mass of the original star is, let's say, 25 solar mass? What if the mass of the original star is 40 solar mass? What if the mass of the original star is 30 solar mass? That is 30 times. If that is the case, then the neutron star that will be formed from that huge 30 solar mass star or 40 solar mass star, that neutron star will have a mass which is larger than this, which is greater than 3 solar mass. So if it is more massive, by it I mean if the core remnant is more massive, approximately 5 solar masses or more. So if the core remnant, now the core remnant is gonna form the neutron star, right? It was supposed to form the neutron star. But if the original star is too large, way too large, like 30 times the mass of the sun or 40 times the mass of the sun, in that case, its core remnant will also be too large. Its core remnant will be approximately 5 solar masses or more. So approximately 5 solar masses or more means like very large mass, right? So since it is very large mass, 5 solar masses or more, it collapses further into a black hole. So it collapses further into a black hole. That is, you see, for a neutron star to exist, it's gonna be like all these huge, like this huge, all this large mass in a very small space, all these neutrons bunched up together in a very small space, right? But then if the mass is even more, like 5 solar masses or more, the mass of the core remnant is 5 solar masses or more, then it will be way too much. The gravitational pull of 5 solar masses, understand this, the gravitational pull of 5 solar masses is like 5 suns. Just think about it like this, the mass of 5 suns. So the gravitational pull of 5 suns, but in the space of like the earth, in that small volume, right? Can you imagine this? 5 suns in the space of earth. Can you imagine that? So if that's how dense it is, and if that's how much gravitational pull it is, then it will not even be a star anymore. It collapses. Now here again, remember how I told you how the universe started? Well, the universe started from a point of singularity where something happened, and then all the laws of physics as we know it were formed, right? In this case, something happens and a black hole is formed, and we have very little knowledge of what it is, how it works, what's the physics there. Very little knowledge. Black holes. Black holes are the biggest gravitational fields of all time. Like, there is no gravitational field stronger than the black hole in the entire universe. Black holes are the biggest gravitational fields. Like, they attract everything. The gravitational field of a black hole is so strong. Read this line with me. The gravitational field of a black hole is so strong that even light is unable to escape from it. Even light. Like, normally you think of light as light is the fastest thing in the universe. Like, no, nothing stops light, right? Nothing stops light, right? But like, gravity actually bends light. That you will study in general relativity if you study that, Einstein's general relativity. But the point is, black holes have such strong gravitational fields that even light cannot escape from a black hole. Now, last year we had an image of the black hole, and now you might be asking, wait, what? This doesn't make any sense. We take photographs by using light, right? So you're saying black light cannot escape from a black hole. Then how did we get a photo of the black hole? Well, guess what? That's not a photo of the black hole, to be specific. That's actually a photo of something called the event horizon of a black hole. You saw a circle, right? That circle is basically all the light that has bounced back from objects that are very, 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 very close to the black hole. After that line, you saw a circle with a black ball inside the circle, right? So that circle of light we can see. Beyond that point, light cannot escape. So that's the light cannot escape from the black hole, but light can escape from a slight distance from the black hole, and we see that distance. We see the light from that distance as a circle. Okay, well, it's not actually a circle, it's actually a sphere, but um, if you think about it, if you see a ball from a very, very large distance, it will seem like a circle. Okay, and also there are other things like bending of the light behind the sphere, and then, oh, I won't get to those details is here. And that black holes picture is the actually the cover page of your booklet that you got. So yeah, check that out if you haven't already. So yeah, okay, so that's supernova, neutron star, black hole. So to sum it up, red supergiant to supernova. And then from supernova, there are two possible cases. Either the core remnant, either the core remnant is 1.5 to 3 solar mass. In that case, it will become a neutron star, or the core remnant is more massive, like approximately 5 solar masses. In that case, it collapses into a black hole. And what is that black hole? The black hole is again another singularity. That is, it's where our equations become like, it's a mathematical term, singularity. You will learn this term in like for a very, very rough rudimentary say will be something like, you know how 1 over 0, it's undefined, right? It's not infinite, but it's undefined. Okay, so kind of like that, right? Like, the every all our equations become singular at that point. Like, they become unsolvable there at the black hole. So it's another singularity. All our equations become like the gravitational equations, the Einstein's gravitational equations, they become singular at the point of singularity, the Big Bang theory that we will study later. But they also become singular at the black hole. So black hole is a so you can think of black hole as an infinitely strong, nearly infinitely strong gravitational field, although it's not actually infinite. You can think of it like it's nearly infinite because we cannot really calculate it totally, but You can think of it just for the like sake of it, because there is no other gravity like it. Okay, like there is no other gravitational source as strong as the gravitational field of the black hole. So, and by the way, when I say the black hole, it's not like one black hole. Okay, there are like billions of black holes. Okay, just like there are billions of galaxies. Like we were talking about stars, like, right? So there are billions of stars, and all of those billions of stars are in a galaxy. In our case, it's the Milky Way galaxy. So all of those stars are in the Milky Way galaxy, and now you know that the planets orbit the star, right? Planets orbit star, but what does the stars orbit? The stars actually spiral inward. In our case, it's our Milky Way galaxy is a spiral galaxy. There are other shapes of galaxies, but in a spiral galaxy, the stars in our galaxy, all the stars are basically spiraling inward towards the black hole. Like if you remember from your last class, if you remember this diagram, like from your very first class, you remember the Milky Way galaxy? Do you remember that? The Milky Way galaxy picture I showed you, and I showed you the center of the galaxy. So that center of the galaxy is our black hole. Okay, that center of the galaxy is a black hole. Okay, I'll just show it to you for a second to help you recall that. Just hold on a second. Yeah, you saw that in part one, right? In this lecture, you remember this lecture? So yeah, remember we pointed here, this pointer, the center of the Milky Way galaxy. That will be our black hole. And see, the Milky Way galaxy is a spiral galaxy, right? So all the stars, the billions of stars, every dot in this picture is a star, right? One of those dots is our sun. So all of those stars are basically spiraling inwards into the black hole. To understand what a spiral motion is, if you don't get it, what I'm trying to say, just turn on your tap in the basin, right? The water basically spirals inward into the like hole, right? So similarly, like that, all the stars are basically spiraling inward towards the black hole. So what happens when a star gets into the black hole? Well, it disappears from our sight, because we can only see stars because light reaches our eyes and our telescopes from the stars. But once a star enters a black hole, then that light will not be able to escape. So that is the main reason we do not know much about black holes, because you see, unlike every other object in the universe that we know about, we mostly know about them because of the light that they emit, or the radiation that they emit, which is basically light. So for example, like the sun is emitting yellow light, another star is emitting red giant, so red light, another star is maybe supermassive because it's blue light, and also different frequencies. From the information of light, we get all the information about what nuclear reactions are taking place in those stars, etc., what their gravitational field is like. We get all the information from basically light. And the problem with the black hole is we do not get any light directly from the black hole. We can only get light from something called the event horizon. Event horizon is the last dot in the around the black hole that we can see. Imagine it like this. um, if you draw a circle, imagine you draw a circle on the floor, okay, and you say you're playing this game with your friends, and you say like, whoever steps inside that circle disappears, okay. Then all of you like stand at a distance from that circle, and then one friend walks towards that circle. What's gonna happen? Right when he approaches the circle, he approaches the black hole's event horizon, that circle. When's the last time you're gonna see your friend? The last time you're gonna see your friend is when he is just at the circumference of the circle. Right when he steps in, he disappears. Because, not disappears, actually, in case of black hole, what happens is when he is at the circumference of the circle, light from him is still reaching our telescopes and our eyes. But once he enters the black hole, no more light can escape, so we cannot see him anymore. So goodbye, your friend. And that's all about black holes and neutron stars from here. But we will study more from. We will also go through this reading material. But before that, I would like to answer some of your questions. Do you have questions? Of course, you have a lot of questions. It's fun stuff. Okay. Where is it? Okay. No. One report. Solar mass, the mass of our sun. Yes. One solar mass. Well, I gave that value to you like numerous times. 2 into 10 to the power 30 kg. That's the one solar mass. PDF Devo. Um, I'll give the updated PDF. Don't worry about it. One solar mass as long as yes, 2 into 10 to the power 30, 1.989 to the power 30. Yes. Okay. Okay. So any questions? So it needs more density to become a core remnant. 1 point. Yes, it needs to be very dense to become a black hole. Like basically, it's the most dense. Core remnant 1.5 solar mass হবে নাকি 5 solar mass হবে এটা কিসের উপর ডিপেন্ড করে is the solar mass if the actual original mass of the star is 15 to 20 solar mass, then the mass of the core remnant will be 1.5 to 3 solar mass. But if the original mass of the star is much higher, for example 25, 30, 40 solar mass, then the mass of the core remnant will be 5 solar masses approximately. So what will be the mass of the core remnant depends on the original mass of the supermassive star from which the supernova occurred and from which the core remnants are. Okay, I hope that answers the question. Yes, there are many black holes in our universe. One of them in our galaxy, the Milky Way. Like I said, event horizon. I think you asked that question like 10 minutes ago, but I think the event horizon is now clear after the uh, circle example. Please ask again if it's not clear. No, we can't touch any star. You can try though. Sorry about that. Then why doesn't the black hole engulf the universe by gravitational pull? Excellent question. Then why doesn't the black hole engulf the universe by gravitational pull? Well, it is. It is engulfing the universe by gravitational pull. But the universe is huge. Like not just one black hole, all the black not like universe, like every black hole is engulfing all the matter in that galaxy that it is in. Okay, so yeah, all the stars are spiraling inwards into the black hole. So eventually the stars will end up in the black hole. Yes, yeah. Eventually a galaxy. That's how a galaxy ends. That's not in your syllabus, but that's how actually a galaxy ends. All of the stars eventually get into the black hole. But like you can see the time scales, right? It will take 5 billion years for the sun to become a red giant. And like so you can imagine how big a time it will take for all the stars in a galaxy to die and then get engulfed by a black hole. That's a huge time. So, yeah. Yes, math error 1/0. That's what you're supposed to get because it's undefined. Neutron star or black hole, only one of them will form. Both of them won't form. If the mass of the core remnant is 1.5 to 3 solar mass, a neutron star will be formed. If the mass of the core remnant is approximately 5 solar mass, then a black hole will be formed. Approximately 5 solar mass or more, then a black hole will be formed. Um, Come on, this is 20th century. Still, we got stuff that are unsolved. What did modern astrophysicists and physicians did? Everything you're studying here is modern astrophysics. By the way, these are not like. By the way, like astrophysics is the only topic where like not the only topic, but it's one of the topics that you're studying like the latest contents. Okay, like for example, I'll tell you like a few classes later that the universe is accelerating. The expansion is accelerating, and we came to know that like in what 2005 or so, just this decade, like the previous decade, just okay. So like this is latest and greatest stuff. Okay, so it's still being discovered. A lot is still being known. Okay, like if you really want to stay updated, which I try to, like before your classes, I try to watch a few lectures of MIT professors, of astrophysics and quantum physics. They actually they are actually researching about this stuff and coming out with new and new observations and conclusions. No, no, no. All of these are not done by people of our grandfather time. Actually, no. Like these are be after Einstein. These are from 1990s to 1990s, 1980s. That's the time where we got to know about all these things, neutron stars, black holes, and everything. What happens if two black holes collide? When two black holes collide, basically their gravitational fields combine and they form a larger black hole. And a huge gravitational wave is sent out. So attraction of black hole is what happens after supernova becomes a black hole, like a dead star becomes nebula, and no, no. Oh, okay. Very good question. What happens after supernova becomes a black hole? Well, after supernova becomes a black hole, that's the last stage of that star's life cycle. So nothing else after that. So the second part of your question, like as a dead star becomes nebula and nebula become a star. Yeah, understand this. Like a white dwarf becomes a cold black dwarf. It never becomes a nebula. But when the star explodes, like in the planetary nebula, that's when the nebula is formed. But similarly for these massive stars, when the remnants are thrown away into the universe, into empty space by the supernova, not the core remnants, the other remnants are thrown away into space by the supernova, that forms the nebula, the stellar nebula. But the core remnant forms the neutron star or black hole. So the core remnant forms the neutron star or black hole. It doesn't form any stellar nebula. The other parts of the supernova form the stellar nebula. I hope that is clear. Which is the largest star? That's a question for Google. Like you just, yeah, you have a click for a supergiant. We're struggling to get of our solar system. Can black holes destroy the universe? No, like I said, it will engulf, but slowly, very slowly. So whoever can fit anything in that circle, you will. I see that. I get that. It's a Mr. Beast joke. Yeah. Why don't we experiment by putting some? Because you can't get there. After engulfing, where will all of that end up in? And we will. Where will that end up in? Very good question. We don't know yet. We need to find out. Maybe you will find out someday. Who knows? Parallel universe. We don't know about them yet. I think. Oh man, the connection's dropping again. Sorry about that, guys. Yeah, Bangladesh internet still not good. Yeah, I think the connection is. Once again, thank you for your patience, guys. Once again, thank you for your patience. The connection is back online. There was some lag. Sorry about that. When can I study celestial mechanics? The lag is fixed now. Please check. Celestial mechanics, you can study it in your as your university major topic, like your undergrad, mostly masters. Like I guess you need to do undergrad in astrophysics and then go ahead and or just physics, pure physics. You need to do undergrad in pure physics and then for masters you go to celestial mechanics, astrophysics, etc. Yes, black hole will always remain as black hole. Yes, just like a neutron star will always remain a neutron star, and just like, okay, you may get lag again. Sorry, I don't know why today the internet is being like really like, yeah, you're. Are you guys getting lag again? Um, it, yeah, okay. I think it's fixed now again. Let's check. Alright, why don't we do experiment by putting someone through a black hole? Like I said, you can't. Like, you can't even go past your solar system. You can't even go past, like, Neptune. And you expect what? Like, going to a black hole, passing billions of stars and billions of solar system into the center of the galaxy? Yeah, good luck. Um, call. What is a blazer? What kind of what? What is it? I'm not sure what that question is. Can a black hole engulf a neutron star? Yes, a black hole can engulf anything that you can think of. Anything exists like no, nothing exists like white hole, as far as I know. Can we cross black hole if we travel faster than? Well, impossible, and also I don't even know. Like who knows? Like we don't know because we don't know the physics behind inside the black hole. So yeah, we don't know. Okay, now let's get to our reading material. The reading material that Edexcel actually recommends. So yeah, you will find that everything that I discussed, most of it, a lot of things will not be here. So like Edexcel has shortened this up syllabus. But anyway, we study for the fun, not for the syllabus. Okay, now this is a picture of the Crab Nebula. In 1054, a star in our galaxy exploded as a nebula. A star in our galaxy, so a star in the Milky Way. This is a picture within our galaxy in the Milky Way. For 2 years, it shone more brightly than the sun when viewed from Earth. Can you believe it? Brighter than the sun. Seriously, like brighter than the sun. And it is like what, hundreds of times farther away than the sun, because like it's definitely not in our solar system. It's another star in our galaxy, but sadly it's in 1054 so like long ago. You do understand, right? This is a year. Like now it is 2020. This was 1054. So this is literally 1,000 years ago. Okay. Now all that can be seen now is the huge cloud of debris, which is known as the Crab Nebula. See, this is what I'm talking about. What happens after a supernova? The core remnant will form either a neutron star or a black hole, but the debris, the debris will remain, and it's a huge cloud of debris, like the huge cloud of debris, and that will remain as a nebula, more specifically a stellar nebula, and they have named it Crab Nebula. They just give names whatever they like. Take us these just the names just depend on which astrophysicist discovers them first. Whoever discovers it first literally gives the name whatever he wants. Okay, now at the center of the nebula is a neutron star. See, so that means this star had a this star, when it exploded in a supernova, it had core remnants of 1.5 to 3 solar mass, right, in that range. That is why it did not become a black hole. It became a neutron star. The core remnant became a neutron star, but the other debris remained as a huge cloud of debris all around it, and that's the stellar nebula. So a neutron star. Now look at this data. I love this data. About 30 kilometer across. 30 kilometer. Can you believe it? Like the diameter is only 30 kilometer. You know how small 30 kilometer is? Let me give you an idea. Dhaka to Cox's Bazar is like, I don't know, more than 100 kilometers. So like 30 kilometer in diameter. And this is a star. This is a neutron star. This is one of the densest material in the universe. Just think about it. 30 kilometer diameter. Think of a 30 kilometer diameter ball. Okay, for a better reference, let me give you this. The Earth has a diameter of 12,800 kilometer, and this neutron star has a diameter of 30 kilometer. Okay, and it is spinning at 30 times per second. That's just the spinning speed. Yeah. You may ask, why is it spinning? Because of all the energy from the supernova explosion. That energy, it's still dissipating away. Okay, like that's huge energy. Okay, now let's read about the neutron star and black hole. In the later stages of its evolution, do we have lag? No. Okay, great. In the later stages of its evolution, the gravity of a large star can compress its core until it is only a few tens of kilometers across. Okay? So, in the later stages of its evolution, the gravity of a large star can compress its core until it is only a few tens of kilometers across. So, it compresses the whole star after the supernova. It compresses the core remnants of the star to a very small space, like few tens of kilometers in diameter. Across just means diameter. Okay. Sometimes as a result of a supernova explosion, this produces a tiny, very tiny, so very small in volume, but rapidly spinning, very fast spinning, like 30 times per second. Say that's very fast spinning. Star known as a neutron star. So a neutron star is, they didn't talk about the density, but we already talked about the density. A neutron star is a extremely dense. Yes, the neutron star is at the center of the nebula. So the neutron star is extremely dense and very fast spinning, rapidly spinning, and it's very tiny. Okay. Then black hole. Eventually, some stars become so small and dense that their gravitational fields are so strong that not even waves of light can escape. Like we said, so if it becomes too small and too dense, for example, like if it becomes this small, like tens of kilometers, but its mass is like 5 solar mass approximately, so that's huge density, very dense, then the gravitational fields become so strong that not even waves of light can escape. these this star word should be in quotation marks because we don't really call them stars, but yeah, these quote unquote stars are therefore called black holes. Okay, so black holes are basically extremely small but extremely dense gravitational fields. Okay, although they emit no electromagnetic radiation, their gravitational fields can pull matter in from nearby stars. This material can glow brightly as it falls into the black hole. So this is how we see the event horizon of the black hole. We see the event horizon because, understand this, let me highlight some parts here. Black holes, they emit no electromagnetic radiation. There is no light, no infrared, no ultraviolet, nothing. They emit no electromagnetic radiation. However, their gravitational fields, what does it do? It pulls matter in from it pulls, I'll just say, it pulls nearby stars. So it pulls nearby stars. It pulls basically matter in from nearby stars. So it pulls the stars, nearby stars. This material, what happens when something travels very fast? It actually gives off energy as light. Okay, so this material can glow very brightly because they get really hot. Like traveling at this very high velocity, they get very really hot. So they glow very brightly as it falls into the black hole. So when we see the event horizon, we don't actually see light from the black hole, we just see light from the event horizon, from the material that is getting pulled into the black hole very fast, and those materials are glowing very brightly. Is that clear? For this is an artist's impression. Like this is not a picture, it's a drawing. Okay, it's an artist's impression. Sorry about that. So the artist's impression is actually based on like whatever everything that we know about the black holes. So which is we believe to have a black hole orbited by a blue supergiant star. So a blue supergiant star is being drawn into the black hole. Okay, material is constantly being pulled into the black hole by its enormous gravity, producing X-rays as it accelerates towards it. So as the material accelerates towards it, it emits electromagnetic radiation such as X-rays. Cygnus X1 is the brightest source of X-rays in the sky after the sun. So like we get a lot of X-ray from the sun because it emits all the electromagnetic radiation, but this is a very bright source of X-rays because it's really bright. You see, it's emitting from a black hole. That's the event horizon, the circle around the black hole that you see. Okay, now so any questions thus far? If you have any questions, I'll answer those, and then I'll get to these checkpoint questions. Um, mm, can a black hole engulf a nebula? Yes, a nebula is just debris, large debris. So yes, a black hole is constantly engulfing nebula. Like I said, a black hole engulfs everything. So don't ask that question. Can a black hole engulf? So if you say, can a black hole engulf blank, like insert anything in the blank, the answer will always be yes. Okay. Now, have to wait for the physics of black hole? No, we don't have to wait for the physics of black hole. We have to find out and figure out the physics of black hole. You guys will. We will do this. Okay. So I'm not sure what you mean. Edexcel. Can anything travel faster than light? No. Can a black hole? The answer is yes. 60 years later, we can see black holes still same as 2018. What gives the black hole the ability to engulf everything? What gives the black hole the ability to engulf everything? Its insanely high gravitational field. Neutron Star orbit correct. No, nothing actually orbits. Well, the space debris, the nebula or debris, kind of orbits. Not really orbits the neutron star. But yes, the neutron star is at the center of the nebula. John Bevis discovered, but it was named by William. Oh, okay. Does black hole orbit at a regular path, such as planets do? Black holes orbit other black holes only when there are a pair of black holes. Okay, so it's kind of like that. Otherwise, they're just engulfing other matter and material. What is the gravitational field strength of black hole? Nearly infinite. Why time doesn't work in black hole? Very good question, excellent question. Because the higher the gravitational field strength, the slower time gets. Like time travels slowly as the gravitational field strength increases. So as black hole has nearly infinite gravitational field strength, so time should nearly stop in a black hole. Nearly. Is black hole the largest object? It's not even an object actually. Don't say can't a black, like I said, a black hole can engulf blank. Insert anything in the blank, the answer is always yes. sun, star, nebula, neutron star, whatever you say. Yes, it can be anything. You do know the meaning of the word anything, right? When I say anything, I mean anything. Yes. Okay. Now, now let's check out these checkpoint questions. Before we go to cosmology in the next class. So, until we go to cosmology, you should be able to do these checkpoints. Like this will be a full review of everything that you have studied so far in astrophysics. Okay, I'm not gonna bore you with these ones. I'm gonna ask you these ones first. Okay, let's go through this. Explain what is meant by nebula. Try to recall it in your head before I tell you the answer. Explain what is meant by a nebula. Do you remember what is meant by a nebula? Okay, now let me tell you the answer. Here's the answer. A collapsing cloud of gas, which is the first that represents a collapsing cloud of gas. Um, a collapsing cloud of gas that represents the first stage in the evolution of a star is called a nebula. Alright? As these clouds form and get steadily smaller, the force of gravity becomes stronger and accelerates the process. So, what's a nebula? Basically, this paragraph right here. Okay? So, this is a nebula. The first paragraph of nebula. The next question is, what is a main sequence star? Then red giant, then white dwarf, supernova, neutron star, black hole. So basically all of these. So what's a nebula? That's a nebula. What's a stable main sequence star? When the radiation pressure is strong enough to balance the gravitational forces, then a stable star is formed, and that stable star is called a main sequence star. Then what is a red giant? What is a red giant? Like this whole thing. If I want to say it in short, it will be um, when when I'll start with in a main sequence star. In a main sequence star, when the hydrogen fuel required for nuclear fusion, when the in a main sequence star, when the hydrogen fusion fuel required for nuclear fusion runs out, the core of the star begins to collapse under the relentless pull of gravity. This increases the temperature, pressure at the core of the star and allowing it to start fusing. So the star starts fusing helium to produce more energy and therefore radiation pressure. So it produces more energy and radiation pressure in its core. Okay, to fuse helium in its core word is important. So then this radiation pressure pushes out the outer layers of the star, causing it to swell up dramatically. And then as the outer layers of the star are now much farther from its core, so they cool down and only glow with a red color, thus forming a red giant star. So that's a red giant star. And then what is a white dwarf star? Eventually the thin outer layers of a red giant star will run out of energy and only the core of the star will remain. This is called a white dwarf star, the hot dense core of a star which has passed through the red giant stage. Then what is a supernova? Stars much larger than the sun form a red supergiant, right? Oh, right. I did not read through this paragraph with you guys. I'll do it now. No worry. Is the connection all right? Yeah, the connection is all right. Okay. So in the 1930s, the Indian astrophysicist Subramanian Chandrasekhar calculated that calculated mind this word calculated that only stars with a mass less than 1.4 times the mass of the sun could end their lives as white dwarf stars. Okay? The force of gravity in stars heavier than this would be so strong that it would continue to crush the star to even smaller sizes. So, stars with a mass greater than 1.4 solar masses pass through other stages of stellar evolution beyond the red giant stage. So, when I say the sun is an average and small star, but then I go on to talk about the other stars. So, remember this, we talked about two life cycles. One is nebula to average star to red giant to planetary nebula to white dwarf. Another is more massive star, nebula to massive star to the red supergiant to supernova to black hole or neutron star. Now, what is the condition? When I say more massive, how much more massive? Stars with a mass greater than 1.4 solar mass. Okay, so stars that are like 1.4 times larger in mass than the sun or more, those stars will undergo beyond the red giant stage to a supernova. Okay, so red supergiant and then supernova, like we have studied here. Okay, so what's a supernova? Stars much larger than the sun form a red supergiant as these stars collapse. Okay, so I will say what's the supernova? As a red giant star collapses, matter is compressed beyond the density of a white dwarf star. It becomes very unstable. They have skipped through all the fusion stuff, and this caused the star to explode as a supernova. Simple, okay? This throws dust and gas into space, forming a new nebula. When this happens, the star can become as bright as a galaxy for a few months. For a few months, the star becomes as bright as a galaxy. Yeah, very cool stuff. And then what's a neutron star? Well, in the later stages of evolution, the gravity of a large star can compress its core until it is only a few tens of kilometers across. Sometimes, as a result of supernova explosion, this produces a tiny, rapidly spinning star called a neutron star. Then, what's a black hole? Black holes, well, eventually stars become so small and dense, and their gravitational field is so strong that even light waves cannot escape. These stars are therefore called black holes. And then if you move on to the next question, key stages. Identify each of the following stages of stellar evolution from these descriptions. A stable star-like sun. What is this? Main sequence. A star compressed by gravity until it is only about 30 kilometers in diameter. So tens of kilometer in diameter only. What's this? This is the smallest that we have seen. Tens of kilometers in diameter. Neutron star. A cloud of hydrogen nuclei collapsing under its own gravity. Just a cloud of hydrogen nuclei that is collapsing under its own gravity. What's that? A nebula. And then a large but cool star which has run out of hydrogen fuel. So it's large but cold, and it has run out of hydrogen fuel. It has not totally run out of fuel, okay? You have to notice this word. It has run out of hydrogen fuel. If it said that it's a cold star, small star, run out of all fuel, that will be white dwarf. But it's a large star, but cold, and it has run out of all fuel. So it has run out of only hydrogen fuel. This is a red giant. Okay, so I'll tell you the answers again. Main sequence. Then what is this? Neutron star. What is this? Nebula. And then this is red giant. Okay. Okay, that's it. And next class we will start cosmology. So, any questions thus far? Any questions? if I throw myself into a black hole, I assume you will grow old, but I will stay the same. Yes, technically yes, but if you throw yourself, you will die because your body will get stretched by the gravitational pull into a, like, you will get stretched until your diameter is like that of a hair. Okay, can a black hole engulf another black hole? Yes. Can you guys stop asking questions like can a black hole engulf? I told you it can engulf anything, even a black hole. Yes. Yes, they combine. So yeah, they combine meaning basically engulf each other. They engulf each other. Okay. Okay. So no more questions. Really? No more questions? These are fun stuff. Come on, guys. No more questions? So, oh, okay. There are questions. No, actually, because it absorbs all the light. Why black hole is black? Because it absorbs all the light. Like light does not escape from it. So, it's the absence of color. Absence of light is black. Supernova की super red giant है ना? No, the red super giant, red from a red super giant we get a supernova. Not the other way around. Supergiant from a supernova, we get a supernova from a red supergiant. I hope that makes sense. Like the sequence is nebula, massive star, red supergiant, and then supernova. Okay, I'll repeat. No, not red supergiant from supernova. No, the sequence is massive star, nebula to massive star to. I'll show you the sequence. Like you have seen the sequence here. Um, This is the sequence from nebula to massive star to red supergiant to supernova to neutron star or black hole. So, guys, at the end of the day, you'll for your exams when they ask you the question like describe the life cycle of a star, you mainly need to write these. Okay, these words carry the most marks. So focus here very much. Okay, what's the life cycle? There are just two life cycles to remember. Just two. That's it. A low mass star, a high mass star. What's the life cycle for a low mass star? Nebula to average star. So I'll actually write it here. Sorry about that. This average star and these two are basically. Oh, you can see it. But hang on, you'll see it in a minute. Oh, damn it. Alright, so basically, when I say average star or a massive star, what is this? This stage is the main sequence. Okay? So, it's called the main sequence, the stable state of a star, right? So, from nebula to main sequence, for a small low mass star, it's nebula to main sequence to red giant to white dwarf. You don't need to write planetary nebula in the exam, but you can write it if you want, not no problem. Or for a massive star, it's nebula to main sequence star, that is stable state, to red supergiant, to supernova, then either a black hole or a neutron star. Don't write like supernova to neutron star to black hole or supernova to black hole to neutron star. Don't do this. Don't. Do what? Nebula to massive star, that is to main sequence. For a massive star, nebula to main sequence to red supergiant to supernova, then either a black hole or a neutron star. That's how you need to write it. Either a black hole or a neutron star from a supernova. It's either of the two, not both. Okay, back to your questions. Supernova की super protostar की जानी protostar Protostar is in between the nebula and the main sequence. In between nebula and main sequence is the protostar phase. It's this one. If you look at this diagram, you'll remember. Like from nebula, we get this very small star. It's like a baby star. We at first get this very small star, and then once its gravitational force is balanced by the radiation pressure, then it's a big normal main sequence stable star. So it's in between. The protostar phase is in between the nebula and average star. Again, nebula and main sequence. In between nebula and main sequence is the protostar phase. Again, you don't need to write this in the exam. You just need to write nebula to main sequence. Don't write average star or massive star as the stage. This is to remind you of the life cycle. Like this is the life cycle of a average star or a low mass star. This is the life cycle of a large star or a massive star. Okay, or a more massive star than the sun. This is the life cycle of a sun-like star. Exam questions also ask you like this. This is the life cycle of a sun-like star. This is the life cycle of a star much more massive than the sun. Okay, so nebula to main sequence to red supergiant to supernova to black hole or neutron star. Next class will be on Sunday or Monday, inshallah. Either Sunday or Monday. So black holes and gravitational field strength, Bartlett, time t comet. Gravitational field strength. The stronger the gravitational field strength, the slower time passes, not time decreases. You say time comet. No, time doesn't decrease. Time only increases, but time only passes, but either slowly or faster. The greater the gravitational field strength, the slower the time passes. Can a black hole itself gets engulfed by something else? Another black hole. So why don't we dump our garbage in black hole? Because it's very expensive to dump our garbage all the way to black hole. How can we can't even dump our garbage past like the solar system. We can't even get very far with the spaghettification occurs in black holes. Yes, spaghettification. You can look it up and you'll get the details there. You will say it in the PDF that the supernova from red giant check. Yes. Yeah. Like they said, in the PDF, it's written that nebula to massive star in main sequence to red giant to supernova. They skipped the red supergiant part, but they actually did say red supergiant as well. Later on, you'll see. Let me just show you. Um, that is why you need to read both. Okay, at home you must read both. Don't just rely on my slide and don't just rely on the reading material, the PDF. Read both. Okay. Let me show you this again. So stars with mass pass through other stages beyond the red giant stage. Okay, beyond the red giant stage. So like for normal low mass star, it's red giant and then white dwarf. But for stars with mass greater than the sun, like greater than 1.4 solar mass, these stars go beyond the red giant stage. So what's beyond the red giant stage? Beyond the red giant stage is red supergiant. First it is red supergiant, and then as the red supergiant collapses, it forms the star explodes as a supernova. So supernova always occurs from a red supergiant, not a red giant. Remember this. Other planets or sun, well, right now what we can dump it in space, and it's called space. There's a term for it. It's called space waste or something like that. Yeah, we actually have a lot of space debris out there. Okay, we have dumped a lot of things in space, like a lot of rockets. We have dumped a lot of rockets into space before we could reuse rockets. We used to just dump them in space. So yeah, so there are a lot of space waste. You can look it up and read up on it. There are problems with space waste as well. Where do all the things go once? Little do we know. Where do they all go? We don't know. Okay, so that is it for today. Thank you. Allah Hafiz. I'll see you on either next Sunday or Monday, inshallah. Bye bye. Stay safe.